Well, hi everybody. Today we have Carsten Weidner. He's one of the new postdocs. Well, he's been here since November, so not that newish, but well, he defended in 2006 at the University of Bonn, and then he went to Chile for 2 years as postdoc at the Pontificia. And then he has spent his last 4 years at St. Andrews, and he's going to speak about this last work there.
Okay, hello everybody. I'm going to talk a little bit about stellar initial mass functions in star clusters and in galaxies. And this is work I already started during my PhD, and I'm still following also all these years of postdoc. And so first I want to look with a short overview what we know about the stellar initial mass function, what the stellar initial mass function actually is. And the stellar initial mass function describes the burst distribution of masses of stars. So it's the number of newly formed stars per mass interval. And a typical picture of the IMF is shown here as the so-called Krupa IMF. So here we have the logarithm of the stellar masses, and here the logarithm of the relative number of stars per stellar mass. And the red line is the so-called Krupa IMF, which is very steep power law for high masses, and has a turnover in the 0.5 solar mass regime, and then downturn towards the brown dwarfs. And so this is like the typical equation shape for this mass function. And so the slopes shown here, 2.35, the Salpeter slope is actually for the exponential version. In the double logarithmic, the slope is 1.35. And why is the stellar initial mass function important for astrophysics? This is shown here in blue, because this shows the number and masses of stars in a certain fraction if you integrate over this mass function. So this line here above, which shows 8 solar masses, above this, for this mass function, we only have 0.3% in number in stars, but nearly 20% in mass. And all these stars end up as supernova type 2 and release most of their mass back into the interstellar medium, enriching it with alpha elements and oxygen. And so they for further generation of stars. While the intermediate mass regime between roughly 0.8 and 8 solar masses end up at white dwarf, they evolve over Hubble time and return some of the mass into the interstellar medium, but with different enrichment. But they are also the progenitors of the supernova type 1a, the main producer of iron in the universe. And these are only about 7% in number, but nearly 40% in mass. While the rest, about 90% of all the stars, are red dwarfs and a few brown dwarfs, about 40% in mass, and they mainly evolve not at all over Hubble time, unless they're part of a closed binary system involved in binary stellar evolution. Otherwise, they're called the so-called lock-up fraction. They just gather material but don't return anything into the interstellar medium. So this regime here is what drives chemical evolution of galaxies, and this is why we're very interested in the initial mass function, especially also for resolved and unresolved populations. So, but why? What do we know about the stellar initial mass function? Where do these slopes come from? And this is a little bit complicated plot, which shows here measured slopes, alpha, and here the center of the bin where this slope had been measured in logarithmic units. And so here you see again the Salpeter slope, 2.3 around here, and this is for the stars between 0.08 and 0.5 solar masses for the brown dwarfs. And all these colored dots and triangles and boxes are different measurements for different young and old star clusters in the Milky Way and in the Large Magellanic Cloud. But as you can see, while they, for example, here cluster around the Salpeter value, there's quite a spread. And the question is, how can we talk about a universal mass function if we see such a spread? But if we take a slide through this plot at about 2.5 solar masses, so shown here is a green histogram, then you can see that first there's the peak at around the Salpeter value. In this case, the peak is 2.36. Actually, if you fit a Gaussian to it, it's very strong. So you can actually use a very tight, very small Gaussian profile. But there are some wings here which are a little bit broader, but have the same center. And if you now compare with models where you just take a number of stars as a star cluster and evolve them dynamically in a computer, you see as a typical result and measure every time steps the mass function, and for different random realizations of the cluster, you actually see the blue histogram. So you can easily explain the observed spread of slopes of the mass function, while still be all coming from the same parent distribution. So the idea is that the mass function in star clusters seems to be universal, with a slope in the high mass end here above 2.5 solar masses salpeter, and all these wings is either dynamic evolution or just statistic noise. So all seems to be clear. We know the IMF resolved in the Milky Way. So these are typical sites where these things are measured, star clusters, like here in the LMC, R1C6. The Orion Nebula, very prominent, very famous. Also OB associations like Cygnus OB2. What is interesting here is that they're all roughly on the same scale, while having a huge range in masses from a few thousand to more than 100,000 solar masses. They're not that dissimilar in physical size. And that will become important a bit later on. So stars seems to form in star clusters, and there are several studies pointing out that there might be 70 to 90% of all stars form in a so-called clustered mode. That does not necessarily mean that these are bound star clusters, because star clusters stars form in a star cluster from a giant molecular cloud with a certain star formation efficiency. And but the rest of the gas is not used up into stars. And when this gas is removed, for example, by stellar winds or supernovae, these clusters can dissolve, because the star formation efficiency is usually measured to be around 30–40%, meaning if you remove the gas, you remove the majority of the potential, and this can dissolve a star cluster. So they can dissolve very quickly, because the majority of the feedback from the stars is very early on, especially if you have O-type stars. They only live a few million years, and then and during this time and at the end put a lot of energy into the medium where they're formed from. And these released stars then just form the normal feed populations. And if you want to study the IMF of a whole galaxy and not just a single star cluster, you have to add up all star formation in that galaxy. And the question is this what we call the integrated stellar initial mass function, the IMF for a whole galaxy? Can this be the same as the IMF which we observe in individual star clusters? And here's already a hint of a problem, because if you consider one star cluster of 1 million solar masses, how could this have the same stellar initial mass function of thousands and thousands of very small clusters, or for example only 50 solar masses? Because we know these things exist. The even smaller things, Taurus Auriga subgroups, are 10, 20 solar masses. And such a group can never have a 100 solar mass star, but we know these massive stars exist. So, but the question is this effect strong enough to make a measurable difference? And here we have to look a little bit into statistics, because the IMF is a very non-symmetric distribution. And if we want to look at the most at stars, the massive stars, we have to consider that the distribution of the most massive star, as shown here, is also non-symmetric, which leads to some that, for example, the mean of this distribution is not very descriptive. The mode, the peak, as all these values are not the same, and the median are all a bit different. And depending on the number of stars, so the size of the cluster, this distribution looks a bit different, and these values change. So in order to meaningfully describe what we can observe in massive stars and star clusters, we have to not only look at mean or mode values, but we also have to look, for example, at this blue range, which between which 66% or 2/3 of all these massive stars should be, in order to see if there's a measurable effect of the of small star clusters on the integrated IMF of whole galaxies. And this is what I done here. Here you see the mass of the measured masses of star clusters in the Milky Way and a few in the Large Magellanic Cloud, and the mass of the most massive star in the star cluster. And so all these black dots are compiled from the literature, but all normalized to the same lower mass end for the overall mass. And if you now would expect that everything is randomly sampled, so then the median for a random sample population, the median of this most massive star is this red line. And obviously the observations do not describe the median very well. The mode is a little bit better description, but if you look at the 2/3 interval, the interval in between 2/3 of all these massive stars should be, you see that there's a big problem for massive star clusters. So,
very quickly.
Yes, sorry, I forgot to mention, these are all very young star clusters. So they're supposed to be not without supernova, like less than 3 mega years old.
Okay.
This is R136 and things
even
like that.
so, the question is whether the very most massive stars are even shorter lived and so on.
I mean, there's some physical limits to how quickly you can burn fuel in the core of a star. So much less than 2 mega years is, at least from what we know from fusion and stellar evolution, not really possible.
Thanks.
And yes, I divided this sample of young star clusters in 3 bins. These are the low mass star clusters, less than 100 solar mass and cluster mass. They are very well distributed around the median, which is nice, but they're all, except 3 exceptions, they are all within the range where only 2/3 should be, which is actually already quite unlikely. There's a probability of only 0.2%, but still they are kind of, could be random sampled. Could be a bias, an observational bias. If you look at the intermediate mass sample, between 100 and 1,000 solar mass, they are obviously not very well distributed around the median. The probability for symmetry about the median of this population is very small. And if you look at the very massive clusters, actually most of them are outside the range where 2/3 should be. This is extremely unlikely. And therefore, we concluded that there is a non-trivial relation between the mass of a star cluster and its most massive star. It could be feedback related, that if you have a cloud of a certain potential, that the mass or these potential is at some point counterbalanced by the feedback of the most massive object. Of course, it's not a one-to-one relation. There's a scatter. I mean, not every cluster and every cloud is identical. They have different rotation, magnetic fields, whatever. But this is quite obvious that this is outside what we expect from random sampling. What we also found here is that there seems to be an fundamental upper mass limits for stars, independent of how massive the cluster is. And this, so we first saw this for R136 in 2004, and Don Feiger showed a similar result for the Arches cluster close to the center of the Milky Way. And so the exact value of this upper mass limit depends a lot on models, and so it could be between 100 and 200 solar masses. It's not that clear, but there seems to, at least that there's not a linear trend further up, but there seems to be a turnover. And otherwise, we would expect everything would be random sampled, and there's no upper limit. We would expect to see a star of several thousand solar masses actually in the Milky Way, as already Bruce Emery pointed out a couple of years ago. So the initial mass function seems not to be scale-free, while the slope seems to be all in the higher mass and salpeter-like. The upper mass of the IMF seems to depend on the cluster mass, and So this means that the IMF is not fully randomly sampled, and this automatically results in that the IMF for whole galaxy, the integrated galactic stellar initial mass function, should be different than the IMF in individual star clusters. The question, is this difference large or very small? And again, here we come back to clustered star formation, and we see a lot of large range in masses, as I've said before, but these ranges are not, these masses are not randomly. There's also a cluster mass function. So also clusters are born in a range of masses which are very well described by a power law. Unfortunately, we don't have a sample which of very young star clusters which cover the whole range of masses in the same object. So this is 3 different environments put together. So we have the solar neighborhood with relatively small clusters, the LMC and SMC in the range of 1,000 to a few 10,000 solar masses, and the antennae galaxy, pair of interacting galaxies with a massive starburst where we have clusters up to 1 million solar masses. But all are very well described by a single power law with a slope of 2.1 maybe, over a large range of masses. And so if we have an event of star formation in a galaxy, it looks like that these stars seem to form in star clusters, and these star clusters are not just randomly, they also follow this distribution, meaning that you have very few massive star clusters and a lot of small star clusters. And this is already important because these small star clusters, as we've seen before, tend to have not as many or not as massive stars as a massive star cluster. A third point here is that we actually can measure a quantity of a galaxy, the star formation rate, and connect it to this cluster mass function. This is a plot we made a couple of years ago with Loren Larsen, who had a lot of very young, most luminous star clusters. This is all the most luminous star clusters in different galaxies. And the red dots are a few have been just recently added after publication. And he used star formation rates from infrared fluxes, and we transformed his luminosities of his most luminous young star clusters into masses. And at this age, the most luminous star cluster in a galaxy is also the most massive one. And yes, you can see the mass of the most massive star cluster scales very clearly with the star formation rate. So if you have a high star formation rate, you have a cluster mass function which is populated up to a certain point, which is set by the star formation rate. And if we know the star formation rate and assume a typical time scale for the formation of star clusters of around 10 megayears, we actually know how much mass is formed, so we can calculate the number of star clusters in which these stars are formed and have an idea about the population in this galaxy. There are a few outliers up here which are also interesting, because they are dwarf galaxies, and in these dwarf galaxies there can also be relatively massive clusters, you can see here, but they have the problem when these massive clusters form and they all these outflows and this feedback of these massive stars and these massive clusters can actually shut down expel the gas from the whole galaxy, from the dwarf galaxy. So you end up with a star cluster which is still there because it needs some time to evolve down here. But the star formation rate already shut down because there's nothing forming anymore, because these clusters probably have shut off the star formation. And then Nate Bastian pointed out that this could be kind of, that these might have started here and just have been pushed over here. And if you now take all these ingredients, which is the relation between the most massive star and its star cluster, the relation between the star formation rate and the most massive star cluster in a galaxy and the cluster mass function, you can actually calculate the IMF of a whole galaxy, which we call the integrated galactic initial mass function. And when you plot this for different star formation rates, you see that this has can have a profound impact on the form and the slope and the upper mass end of the IMF for the whole galaxy. While individually, in all these star clusters where the stars are formed, the IMF has the same slope. It doesn't change at all. The overall integrated mass function, because of all the very few massive star clusters and lots of small star clusters, changes. And for massive galaxies like the the Milky Way and even more massive objects, there's very little difference. But for small galaxies like the LMC, SMC, and smaller, the effect can be quite dramatic. And especially if you have a dwarf galaxy which might not have interacted and forms stars slowly over Hubble time, you can have a completely different mass function compared to a dwarf galaxy which had a burst, an interaction at some point, and had a little burst which had a much higher star formation rate at some point, and at this point it produced more stars, more star clusters, more massive stars, and actually the star formation rate can be so low that there are basically no supernova in this galaxy, or there can be a normal amount of supernova in that galaxy. But this is mainly for dwarf galaxies. Milky Way type objects and larger are not affected by that. So, and this is what we call the IGIMF effect, that you get steeper slopes and a lower mass cutoff for the IMF in your galaxy. And the question is, so far it's just a lot of theory, but can we observe this? And this is a little bit difficult because this integrated galactic IMF is for all stars ever formed in a galaxy, but of course we only see a present-day mass function. And it's very difficult to disentangle evolutionary effects of the stars, aging effects with initial mass function effects. One hint could be that, for example, in this Tolstoy paper, they found in dwarf spheroidal galaxies hints that there never had been any supernova from stars more massive than 15 to 20 solar masses. This could be, of course, also an effect of that these metals have been ejected from these galaxies, or they have never formed. That's our idea. Then Hoverson and Glosbrook found this using tens of thousands of SDSS galaxies that you actually, so here they have the color of these galaxies, and they used stellar population models to reproduce these colors, that you need a slope independence of the mass. So these are low mass objects, these are higher mass objects, and from this gamma would be, so this 1.3 would be salpeter in this gamma notation. So this is 2.3 in the alpha notation. So you have this for low mass galaxies, who seems to have for these SDSS objects steeper IMF. This turnover here at higher masses is not entirely clear, but it could be that this is supposed to be disk galaxies with star formation, that there are some ellipticals or X-zeros contaminating the sample. That's not entirely clear what happened at this end. Another another thing we use as evidence is the mass metallicity relation of galaxies. This is shown here. Long known, and here in red in observations also from SDSS galaxies, is that here's the mass of a galaxy, and here's its oxygen abundance as a proxy for its metallicity, that galaxies of lower mass have lower metallicity. While for a closed box chemical evolution model within constant IMF and without inflows and outflows, you would actually expect no influence of the mass of the galaxy on the metallicity of the object. If you have outflows, you can, for low mass galaxies, you can put down the IMF, the mass metallicity relations, but not the right curvature, not the right way. While in blue are shown models, closed box chemical evolution models with inflow and outflow, but using our IGIMF concept. And the different symbols just represent galaxies with a different amount of gas left after Hubble time. So, for example, the crosses are gas-free objects, elliptical galaxies, and the open symbols are gas-rich dwarf galaxies. And as you can see, without any with a standard set of parameters, without any twiddling, actually these models reproduce very well the shape and of the observed mass metallicity relation. So again, no supernova here in our scenario. There are no supernova type 2, or very few, so these metals are just simply not produced. Another effect of the IGIMF would be for the far infrared flux, is because the far infrared flux is dominated by B stars. For B stars, the IMF changes less than for O stars. So, but O stars dominate the number of ionizing photons, the H-alpha flux, measured in the H-alpha flux. So you would expect a difference between the H-alpha luminosity divided by the H-alpha luminosity and the far infrared luminosity. For a normal IMF, there should be a difference in our scenario because we produce less massive stars and galaxies with less massive star formation. So with in dwarf galaxies, we predicted this downturn. Something along the line actually has been observed. There was first Moira et al. Looked at the H-alpha surface density versus the H-alpha flux UV divided by the UV flux in a large sample of galaxies, and saw that for the more H-alpha rich galaxies, they have a higher ratio than for the H-alpha less rich galaxies, and concluded that there's a non-universal galaxy-wide IMF. Bit more direct comparable to our models is the Lee et al. Result in the same year. They had a large sample of H-alpha observations as FOU observations of galaxies, and they calculated the star formation rate from the H-alpha and the UV, and divided both these values for each galaxy. And if the IMF is universal and constant, there shouldn't be a difference between the star formation rate measured by the UV and the star formation rate measured by the H-alpha. And this is a straight line. And for for galaxies with high star formation rates, this seems to be quite well reproduced. But for in the low mass regime, for very low star formation rates, there's a downturn. And the blue crosses with the arrow bars are binned observed data. And they could not reproduce it in that paper with the constant IMF and stochastic sampling, but the red line here, this is our IGIMF model, can reproduce this very well. There's been also some more recent work where people try to solve this by stochastic sampling, but it's not completely sorted out, but at least our model reproduces without any effort. Then just very recently, we looked at extreme star formation rates because there have been, or in our model, we are always bottom heavy and produce more massive stars than in a normal IMF. But there have been claims for top heavy IMFs, and mostly extragalactic claims. High redshift work, for example, number of observed submillimeter galaxies. To explain the observed number, a top-heavy IMF would help. Then the relation between galaxy stellar mass and star formation rate shows us bias towards more massive stars. And so several studies, also cosmological studies, found that to explain the cosmological star formation rate, you would need a top-heavy IMF. And also to explain the galactic bulge compared to disks, the oxygen over magnesium, magnesium over hydrogen ratios. And also the gamma team found star formation rate dependent top-heavy IMF in the gamma data. So the question is, how could this relate to our model? Because we always produce less massive stars, bottom-heavy, not top-heavy IMFs. And here, what is important here is that these top-heavy IMF seems to happen mainly when there's a lot of star formation. Submillimeter galaxies are very massively star-forming galaxies in the early universe. And at high star formations, you have very massive clusters. But as I've shown before, the physical size of these clusters is not very dependent on its mass. I mean, this is a factor of 3 orders of magnitude difference in mass, while this thing is obviously physically larger, but it's not 3 orders of magnitude larger. And there, which has already been found by Bruce Elmingin, there could be crowding, especially not of the stars, but during the formation of the star cluster in a giant molecular cloud, there could be crowding of the pre-stellar cores. And so we have massive star clusters with very small radii, we have very high densities, but protostars, or these protostellar cores, have very large radii themselves. So they can collide and merge, and that been Bruce Elmingin worked a little bit and with Shadmiri on this. And this changes the IMF, and they predict a top-heavy IMF for star clusters over a certain mass. And when you include this kind of calculation into our model, then you can actually get, instead of the normal Cooper IMF, you get top-heavy IMFs for very high star formation rates. And this is the whole range of, depending on the star formation rate, you get different slopes for stars above 1 solar mass. The shaded area is for this. A lot of parameters are not very well constrained observationally, so we have this shaded area, which is a more secure parameters, and the dotted is like the most extreme of the possibility of parameters, how the IMF might change in very crowded star clusters. And if you now put in all these measurements I've shown before in the list for evidence for top-heavy IMFs at high star formation rates, you see that some don't work that well, but the majority of results is actually quite well reproduced in our model. And for these two, they have used a different way to describe a top-heavy IMF. They change while we just change the upper mass slope above 1 solar mass, they change the peak of the IMF. And this is not easily directly transferable into a slope change. So to conclude, the integrated galactic stellar initial mass function is a natural result of clustered star formation. If stars form in star clusters, the IMF of a whole galaxy is always the sum of all these IMFs in the star clusters. And if there is an effect, in a sense that the IMF depends somehow on the environment of on the size and mass of the star cluster, the IMF for the whole galaxy has to be different than the one from individual star clusters. We found a dependence on the star formation rate. Very low star formation rates produce very steep IMFs and very low upper mass cutoffs for the IMF. Crowding in superstar clusters can lead to a top-heavy IMF and also to a top-heavy integrated galactic IMF. So these crowded star clusters can produce enough massive stars to affect the IMF of the whole galaxy. And we found a few cases of evidence, even more than I showed here, that supports our idea. Thank you very much.
Then the final question.
Yeah, this alpha 3, okay, where you start to count the shape and the slope, is any hint of the variation of this with the star formation? Where, I mean, not the slope, but the point when you start to count it.
The point. I mean, we use always the same angle point around 1 solar mass. There could be, there's some hints that if you have this very high star formation rates, these very massive starbursts, that you also form a little bit, that you form not only very massive star clusters with top-heavy IMFs, but also less of the low-mass clusters. And then if you have very few low-mass clusters, then there could be an additional angle point in the IMF. But that's not very well studied yet.
Yeah, because this starting, let's say, alpha 3 is very important for most of the stellar population studies.
Yes.
This is the ages where you always...
No, for resolved populations like the Milky Way, where this is all basically calibrated on, it works well with around 1 solar mass.
Yeah, just one point. Just recently, okay, and also within our group, we have found evidence for the steeper IMF in more massive galaxies, which are extremely old. So we are close to this alpha 3 region, let's say, where this starts. Yeah. Okay, so there is like lots of evidences in there recently pointing toward that.
Yeah, but this is a present-day mass function.
Yeah.
So, yeah, we haven't really studied the shape and evolution of the present-day mass function in this model. So I cannot really say what I mean, this is something we want to do, to have a look at this. So I cannot really answer that yet.
When you show this plot of the maximum mass in a given of a star in a given cluster as a function of the mass of the cluster at the very beginning, right? Then the curves flatten so that yeah, exactly. Here the models, right, the median or even the 60% limit turn so flatten, but that's a statistical effect, right?
Yes, this is where they wouldn't, they flat because we put in a fundamental upper mass limit. Oh, in this case, 150 solar mass. If not, this would just straight continue into infinity, and then we would diverge even more from. I mean, it's impossible to make any model with an unlimited upper mass limit and go to get it anywhere close to the observations. Only with a fundamental limit for how massive stars can, at least stars to some metallicity. This is not population 3. This is there are some metals involved here. So these otherwise you just straight on. And this model is just random sampling. You take 1,000 stars, take them randomly from the IMF, and then you add up these stars to get the cluster mass, and then look which is the most massive one, and do this in Monte Carlo like 100 million times, and then you get or you can actually calculate it for random sampling. You cannot do it Monte Carlo like, and then you get these curves. And if you don't include the upper mass limit, then it's never going to work.
Right. No, I was imagining that it was as a statistical effect that
yes, no, sure.
You don't have enough big samples.
Carsten, coming back to this plot, I just want to be sure if I understood you well. So you're saying that the IMF is a probability function, so it's a probability distribution. So are you saying from this plot that the probability of finding a massive star is not it's not the same that what you would expect from the IMF? So you find more massive stars, although at the end they follow the same distribution. So can you expand on this?
So the idea is that the IMF is a possibility distribution function which has 3 parameters. It has a slope, a lower mass limit, and an upper mass limit. And because the lower mass limit and slope is obviously the same, people assume that they can just use whatever upper mass limit they like and assume it is universal. But the problem is if the upper mass end is not free or independent of, then you still have a probability distribution function, but you have a changing parameter of it. So you can calculate the IMF for this changing upper mass limit in independence of the cluster mass, and you then get a probability distribution function for this cluster mass, how many massive stars and how many no mass stars you would get. But you don't get a universal one immediately for all masses.
So it's some kind of a stochastic effect. You mean that you have to recalculate the probability distribution due to the fact that you have very few stars, and that the maximum is the most massive star is what is going to fix your probability distribution. This is what you're saying.
Yeah. Okay. I mean, the problem is that what we are missing is very difficult to miss in the sense that it's all very bright objects. You're missing stuff here, which is all very, very bright. I mean, these stars like 150, 60, 70, 80 solar masses, and still with a cluster of a few thousand solar masses around it, you should be able to see them in the Milky Way if they are there. And I mean, this is what we see. So this is why we conclude that either we are extremely unlucky that in the 3/4 of the galaxy where we can actually see these, I mean, you can see 100 solar mass star pretty far these days. In the 3/4 of the galaxy, you can see we actually only have this part of the distribution. But this is, I mean, the probability is extremely low that all the things we are not observing are all in the unobservable part of the disk.